Record. Yeah. So again, we have this series. We'll look at what happens to the terms of the series eventually by taking the limit of the nth term. Okay, and the limit is 2. Okay, which doesn't go to 0. So what this means that if you expand the series, if you write out the terms of the series, when you go long enough, so I go for long enough, the terms become 2 eventually. So you're adding 2 to itself forever because the limit is 2. A bunch of 2's added forever, that is infinity. So you have a divergent series, which should be common sense. That's what the nth term test says. Okay, now I can't, you have to be careful because this is not true. If imagine, I'll actually tell you guys a story. There was a student, I was telling the story at the end of class, like after class yesterday. I had a student, winter of 2016, and I gave exam, the third exam. The third exam is a long exam, okay? It can't be done in like half an hour. But one of the students finished the test in 10 minutes, turned in the test, so confident, so happy. He's like, I'm getting out of here. And he said he's sure he got an A. Okay, he finished the test in 10 minutes. And that's because there were 10 series on there. And for every one of those series, he took the limit of the nth term and got 0 and said, therefore, the series converges. Guess what he got? There were 10 questions on there. He got 10% out of, well, actually, no, he didn't. No, he did get 10%. Yes, got 10% on there because he answered one of them correctly, and that was the divergence one. One of the series, the limit didn't go to 0, so he said divergent, but for the rest of them, the limit is 0, therefore it's convergent, and that is false. So that's why I say you have to be really careful when you use this test. This test doesn't apply if the limit of a sub n goes to 0. Okay, so let me write. You guys gotta pay attention to the be carefuls that I write down every time, because there's always a couple of students who just ignore these be carefuls, and you have your notes in front of you. Okay, if the limit of the nth term is equal to 0, then we cannot say that the series converges. Okay, negating the hypothesis doesn't negate the conclusion, guys. If A, then B, we cannot say not A, not B. Just think about it. And I can show you an example of why this is not true. The harmonic series. We talked about this yesterday. The harmonic series 1 over n, 1 plus 1/2 plus 1/3 plus 1/4, and so on. the terms of the harmonic series get smaller and smaller. And we know that this diverges, okay? It diverges, but the terms get smaller. Limit as n goes to infinity of a sub n is equal to limit of 1 over n. 1 over n goes to 0 because the denominator gets big. It goes to 0. Okay, so again, here we have a series whose nth term goes to 0, but it diverges. It's not convergent. All right, so please be very, very careful. If a sub n goes to 0, then the nth term test doesn't say anything. You just have to do a different test. The series may converge or may diverge.
Did we find out yesterday that that series diverges?
If it goes to 0, if it doesn't go to 0, then it diverges.
But this one goes to 0 and diverges.
Yes.
But yeah, but my question was, did we prove yesterday? I think we did. Did we prove yesterday that that diverges, or we just know because
What diverges?
1 over n series of 1 over
Yeah,
n?
we proved it's divergent. Where is it? Right here.
Oh, right.
Yeah, we kind of subgrouped the terms, and they're all, each group is more than 1/2, and you're adding infinitely many 1/2s, and that's infinity. Yeah, so we proved that the harmonic series is divergent. But this is in general for any series, not just the harmonic. Yeah, then the series may converge or may diverge. Basically, the nth term test doesn't apply. Okay, we have to use a different test that we're going to learn. We'll learn a bunch of them. Okay. So anytime you have a series, you look at it, look at your series, and in your head, look at the nth term and try to calculate the limit. But what does happen to this thing as n gets big? And if it doesn't go to 0, then you want to do the nth term test. Okay, just write it out. Limit, find the limit and say it's not equal to 0. Therefore, the series diverges, and mention that you're using the nth term test, or also known as the divergence test. Okay, so again, nth term goes to 0. Anything could happen. You cannot say the series is convergent. Got it?
So if n doesn't go to 0, we know it's divergent. But if it goes to 0, we don't know for certain that it's convergent.
Right.
Got it. Okay.
You could converge, you could diverge.
Yeah.
Yeah. And we have to use we have to use a different test. And we're going to learn the next test today. The next test is the integral test. Okay, we have the integral test. We have the comparison tests. There are multiple comparison tests. We have ratio test, root test, and then we have the alternating series test that is designed for alternating series, a bunch of them. Okay, but section 11.3 is the integral test. And the integral test, remember when I introduced the series and the limit of the partial sum, we said that the series resembles an improper integral. Okay, so going back to the beginning of this section. Yeah, right here, this is just like the limit as t goes to infinity of the integral from 1 to t of f of t dt or f of x dx. You can think of a series like, well, you could think of it like an integral. It's not an integral, but it does resemble an improper integral. Find the value of the improper integral. If it's finite, then the series is convergent. If it's not, then it's divergent. Okay, that's the integral test. So instead of finding, instead of looking at the series itself, we'll look at its continuous form, at its integral form. Okay, but before we go over any of the definitions and theorems, I have to go over one definition that's actually not in the book, unfortunately. This is the definition of a positive term series. And an eventually positive term series. Okay, so here we say that series, so again, if I don't write n equal to 1 from 1 to infinity, it by default is from 1 to infinity. We say that this is a positive term series if basically every term of the series is positive. If a sub n is more than 0 for all n, starting with n equal to 1. Okay, for example, the harmonic series is always positive. Every term is positive. Okay, if you were to draw the sequence is always above the x-axis. Okay, it's never going to go below. And then we have what's called an eventually positive term series. So eventually means that at some point the series becomes positive and remains always positive. And we want that because when we are dealing with the series, n goes to infinity. So we don't care what happens with n equal to 1, 2, 3. We don't care what happens with the terms of the series for n equal to 1 through 1 trillion. Okay, we just want the series become at some point, and it doesn't matter when, at some point become positive term. And that's because we are doing integrals. And one of the requirements is that the integrand has to be positive, or it has to be non-negative. Okay, so we say if you have a series, we say this is an eventually positive term series if there exists a capital N. This capital N could be 10, it could be 100, it could be 1 million, it could be 10 trillion. It doesn't matter what this N is. But there should be a capital N such that the terms of the series a sub n. Okay, so again, we refer to that as the terms of the series or the nth term of the series, such that a sub n is positive for all little n greater than or equal to this capital N. Okay, so starting with this capital N, every term is positive. Okay, so this means that if I were to plug the terms of the series, the sequence basically, A sub n, sometimes the sequence is positive, sometimes it's negative, but eventually there exists a capital N such that after this capital N, all the terms are positive and remain positive. Okay. Here, I could just write this out for you in expanded form. Okay, so let's say I have a series. We expand this A1, A2, all the way to A sub capital N. Let's see if I have room. Okay, so up to this point, which is A sub capital N minus 1, terms are sometimes positive, sometimes negative. Or they can all be negative. Okay, we don't care what happens until A sub n minus 1, but starting at A sub n, all the terms are positive. This happens, we have an eventually positive term series. Now, the book, when they write the theorems out, they say assume all terms are positive. They say assume the series is a positive term series, which is such a strong condition. They're imposing this massive restriction on the sequence function to be always positive, but we don't care if the sequence, to be honest, if the sequence is always positive, because as I said, here n goes to infinity, so it can start being positive eventually, because we are looking at the end behavior of the sequence or the series. Okay, we don't care about n from 1 to 1 trillion. Okay, here is an example. This is not a good example because the terms get big and bigger, but the sum of n squared minus 81. This is definitely not an interesting series. And we're not going to be looking at the convergence of it because this definitely diverges. But this n squared minus 81, okay, if you plug, and you could try it out, plug n equal to 1, plug 2, plug 3, until 9, this thing is going to be negative. So it's less or equal than, this is our A sub n. This is less than 0, less or equal than 0 for n from 1 to 9. Okay, again, you can try plugging those values in, but A sub n starting at 10, this is going to become positive. So for n equal to 10, 11, 12, and so on. Okay, so here are capital N. Guys, what's capital N? 10. Yes, capital N is 10. That's what we mean by eventually. Eventually, it becomes positive, means that after n equal to 10, it is positive. What's Alexander saying? Not 9 because yes, 0 is not positive, Alex. It's neutral. All right. So let's talk about the integral a little bit. And again, we need this condition. We need the series to be eventually positive because we're going to be looking at an integral and we want the integrand to be positive. Okay. So what is the relationship between an integral and a series? Let's look at that. Yeah, so let's say we have a, let me write this down, relation. Some people think that a series is the same as an integral. Absolutely not, okay? Be very, very careful. The summation, for example, the summation of 1 over n, where n goes from 1 to infinity, and the integral from 1 to infinity of 1 over x, these are not equal. These are not the same things. They just have the same end behavior. Okay, they behave the same, but they don't have the same value. Let's say we have a series. A sub n in expanded form, a1, a2, and so on. Okay, and we can think of this a sub n. A sub n is a sequence or a sequence function. A sequence is a function. So think of a sub n as your f of n. Okay, so again, for example, if I have the sequence of, or the series of 1 over n, the harmonic series, think of f of x as 1 over x. F of n is 1 over n. Think of f of x as 1 over x. Okay? Yeah. So the continuous form of it is 1 over x. Now, if we draw I'll try to draw this. This is the n-axis. Yeah. So if you graph f of x in continuous form, it is, let's say this graph right here. This is a graph of y equal to f of x. Okay, so again, for example, if a sub n is equal to 1 over n, then f of x is 1 over x, and the graph of 1 over x looks something like that. Okay. Now, if I plot the terms of the sequence, here is 1, here is 2, 3, and so on. A sub 1 is just a point. Remember that the graph of a sequence is discrete. It's just a bunch of points that we plug in. And we did that on when? We did graph a sequence, right? It's just a bunch of points. So this is a sub 1. A sub 2 is this point right here. And we know that these points fall on the graph of f of x. Okay, a1, a2, a3, and so on are a subset of this graph. There are points on that graph. A3 is this point. Okay, so if the graph is 1 over x, this is the graph of 1 over x, then a1, which is 1, would be this point. A2 equal to 1/2 would be this point. This would be 1/3. We would have 1/4 and so on. I hope you can picture that. Okay, so now let's look at the relationship between the sequence and the integral. If I draw, look, you can think of this A1 as A1 times 1. Think of A2 as A2 times 1. Just put a 1 in front of every one of those terms, A3 times 1 and so on. Okay? This A1 times 1, it happens to be the area of the rectangle drawn over this interval. Don't believe me? Let me draw that for you. I'm going to draw a rectangle. Okay? The height of this rectangle or the length. This length is A1. And the width of the rectangle, this width right here is 1, because the difference between 1 and 2 is 1. Okay, so this A1 times 1 is area of that first rectangle. Okay, that's what the first term of the series is the same as, area of this rectangle. I can draw a second rectangle right there that has a length A2 over this interval whose length is 1. Again, that width is 1. So A2 times 1 is the area of the second rectangle. Okay, next rectangle is on the interval from 1 to 4. Right there. Again, the length of this rectangle is A3. So the area of this rectangle, which is A3 times 1, is the third term of our series. Okay, so terms of the series happen to be area of those rectangles. Okay, so the series which is A1 plus.
You go where?
Now we all know Sherelle is not paying attention.
Where? She woke me up at like 5 a.m. She's like, I can't fall asleep.
Okay, just booted her out. All right, so A2 is second term, A3 is third term, and so on. Again, this is the area, the total area of those rectangles. Okay, that's what the series is equal to. All right, but the integral from 1 to infinity of f of x, that is the area under the blue curve. It would be this area here. Okay, again, we have, by the way, we have infinitely many of these rectangles. I can't just draw all of them. Great, I just closed my, hold on, I just closed my notes on my, there we go. Yeah, so the integral is the area, the area under the curve. Under the graph of f of x. Okay. From 1 to infinity. So can you tell me if they're equal? Can they be equal?
No.
No. They are not. Very different. But the integral and the series have the same behavior. Okay. I mean, we could see that. That's the integral test. I will write it down. I will write down the theorem. We are going to prove it, but very intuitive, very, very intuitive. If the integral converges, then it makes sense to say that the series is converging, because the difference between the integral and the series is just these. These are like this little areas right here. You all see that? Those areas, those are finite. Okay. So, and when n gets big, in any case, as n gets big, these like little arrows kind of like narrow down, they get smaller and smaller. So if you have a series, instead of doing the series, you do the integral converges, then the series is convergent. If the integral is divergent, then the series is divergent. Okay, it just works both ways. Again, both the integral and the series, they both converge or they both diverge. Meaning that again, if the integral converges, the series is convergent. Or you can say, if the series is convergent, the integral is convergent. They both behave the same way. Okay, they just don't have the same value. And Alex says, as Alex is saying, can you, asking a great question, can we use this on any series? Unfortunately, no. Okay, we can't. Let me write the integral test. And we'll see when we can use the integral test. So this is the theorem, the integral test theorem. Okay, this theorem has 3 requirements, 3 assumptions that have to be met before it can be used. And it says, let's say we have a series. Okay, and we call, so let sum a sub n be a series with a sub n called as f of n. So call the sequence function f of n. And you want 3 conditions or 3 assumptions to be met for the series. Number 1, we want the sequence, we want the function f to be positive, always positive, or eventually positive. That's the first requirement. So with f of x greater than 0, always or eventually. Basically, this says that the series has to be a positive term or an eventually positive term series. That's what f of x more than 0 means. The sequence function, this thing has to be eventually positive, or it could be positive for all n. Okay, second requirement says that f must be continuous. It must be. continuous on the interval from 1 to infinity. Okay, 1 to infinity because our series here begins with 1. And we need continuity, guys. We need f to be continuous because we are going to be doing its integral. Okay, if the integrand is not continuous, then you can't use the fundamental theorem. The integral is not going to exist if the integrand is not continuous. Okay, so that's one thing. The third condition, which makes sense, should say that f is a decreasing function. We need f to be decreasing, guys, don't we? Because if f is not always decreasing, then we don't have that concept. Well, if f is not decreasing, the series is just going to diverge. Okay, we know that for sure. But we need f to be always decreasing because we want, I want you to think why. Why? It has to do with these errors. It also, that condition is also used in the proof. So f(x) must be decreasing for all x. Okay, or it can be eventually decreasing. It doesn't have to be decreasing always.
Professor,
Yeah,
and when you say eventually decreasing, you're saying that eventually at some point it's continuously decreasing.
yes, yeah. So here is a sequence function that's eventually decreasing. We have a sequence that goes up, then goes down, then goes up. But then after a certain point, it goes down forever. It's decreasing forever.
And the way we can find it, the easiest way is just the first derivative test.
You could, yeah, exactly. Very good. That's how you do that. This is how you check for eventually or for just decreasing. Just do the derivative, first derivative. That's the easiest, and it always works. There are multiple ways that you can check a sequence is decreasing. You could do the first derivative. You can also show that a sub n plus 1 is less than a sub n. This is saying that the next term is smaller than the term before. A term is smaller than the term before. That means decreasing. But first derivative always works. Okay, then the integral test says that the series and the integral both converge or both diverge. They both have the same end behavior, is what this is saying. Okay, so this is really cool, guys. Again, this says that if the integral converges, then the series converges. If the integral diverges, then the series is divergent. Or it can be used the other way. If the series is convergent, then the integral is convergent. Or if the series is divergent, then the integral is divergent. Okay. Hold on, AJ. I'll look at your question in a little bit. So let me tell you guys why this test was discovered, why it was designed. This test, that we are not using this test the way it is used in the math field. Okay, this test is actually used to see what happens to integrals. The test is used to use a series to see what happens to an integral, but we are using it the other way. We are using an integral to see what happens to a series, okay? And the reason for that is because integrals are not easy to evaluate. And an integrand, you could have an integral with an integrand that is really, really, really hard to integrate. Okay, so answering or trying to see what happens to an improper integral is way more difficult than trying to see what happens to a series. Because for a series, there are multiple tests. We just know one of them so far, the nth term test, and we know, of course, the integral test. But there are other tests, like the comparison test, ratio test, root test, that are designed to see what happens to a series. It's easier to see what happens to that than that. So in reality, this theorem is used to see what happens to an integral using a series, but we are using it the other way around. Okay, let me see here what's the question in the chat. It says, question from AJ, could you use it on a specific part of a sequence where it is decreasing, like, oh yeah, AJ, this has to be eventually, the sequence has to be eventually decreasing, meaning that it has to start at some point, it starts becoming decreasing and stay decreasing forever for the rest of the series. Yeah, because we want to know what happens to n to the series as n goes to infinity. We do limits of partial sums. All right, so let's actually look at a couple of examples, and I'll try to prove this if I have time today. If not, we'll prove it tomorrow. Let's go with the harmonic series. Again, I could call this 1 over k going from 1 to infinity, but the book uses 1 over n. They use n. We proved this thing is divergent. Done deal. I mean, we did prove it, but we can also use the integral test. Okay. Divergent, but okay, so the thing with the integral test again is that you have to check all 3 requirements. All right, so here, notice that a sub n is equal to 1 over n. So we let f of x be 1 over x. Make it a continuous function. And the variable n is used when the domain is 1, 2, 3, 4, 5. X is used when the domain is an interval from 1 to infinity. Okay, a continuous interval. So call it 1 over x. If you just leave it as n, it's okay. I mean, who cares? Check the 3 requirements. Again, here, by the way, here n or x is greater or equal than 1, because here n begins at 1, goes to infinity. Okay, so we are on the interval from 1 to infinity here. Okay, check the 3 requirements on that interval. All right, so number one says that the function has to be positive. And there is not much to say here. F of x 1 over x is always positive for all x greater or equal than 1. Right? I mean, there is not much to say, right? This x is 1 or more. So 1 over that is always positive. Okay. Second requirement says that f has to be continuous on the domain of integration, and this function is continuous. The only point of discontinuity of this function is 0, and 0 is not in that domain. So just mention f is continuous. On x or for x greater or equal than 1. Okay? Yeah, a rational function, only point of discontinuity is not in that domain, so we are good. And for the third part, we need to say f is decreasing. And for that, you can definitely, as we said, use the first derivative. Okay, find f prime of x. F prime of x, you can use the power rule. It's negative 1 over x squared. And again, not much to say because this is always not that, yeah, x squared is always positive. It has a square after all. And you have a negative in front of that. So the whole thing is less than 0, which means that f of x decreases for all x. And when we say for all x, it's for all x in the domain of integration, which is more than 1. Okay, we don't even have to be eventually concerned. Okay, you may have a sequence function whose derivative starts being negative after, like, let's say x equal to 100. Then you have an eventually decreasing function. Okay, so this thing doesn't have to be negative for all x more than 1. It could be negative for all x more than 10 if you were to solve it. That could happen. Okay, we're gonna see examples in the future. So since all requirements are met, guys, you need to check all these 3 on. I remember when I was in my interview for this job. Was it this job? Yeah, I kind of applied for a teaching position 3 times. And I remember in one of my interviews, I had to do an integral. I had to do a series using integral tests, and I had to check the requirements. So I heard when some of the other people who were interviewed, I heard they did not check the requirements and they didn't get the job. So I'm letting you know, these requirements need to be checked. So Ari is asking, if we have an eventually decreasing function and it starts decreasing from 100, do we have to change the integral so that it's safe? Not at all. Not at all. You could change the integral to start from 100 if you want. You can still start it from 1 because that doesn't really impact. It doesn't impact the divergence or convergence. Ari, you can have, look at this function. It doesn't matter if you start n at x at 1. So from 1 to infinity, this would be the area, or started from 100. Okay. Either way, we can, this doesn't impact the convergence or divergence of the series. If this area is infinite, right? Then you have infinity plus some finite, which is still infinity. If this area is finite, then you have finite plus finite, it's still finite. So good question, but it doesn't matter. Just start, and yeah, we're looking at just the end behavior. All right, so yeah, that was a great question. So this could be x greater or equal than 100. Let's say you have a function that starts decreasing from 100. You can start your integral from 100 if you want. You can start it from 1. No one cares. The end behavior doesn't change. Okay, so here the integral test. Applies. Okay, do the integral from 1 to infinity of 1 over x. And you're now doing it in proper integrals, so you must do your improper integral properly, okay? Meaning that you have to replace that infinity with a t, do the limit from of the integral from 1 to t of 1 over x. Okay, we are familiar with this integral. Take the integral. It's ln of absolute x going from 1 to t. You can totally drop that absolute value. We've had that discussion before, because here the domain of integration is from 1 to infinity. So x is always positive. Plug in t, you get ln of t. Plug 1, you get ln 1. ln 1 is just 0. Okay, and as t goes to infinity, ln of that goes to infinity. Therefore, the integral is divergent. I should say here implies, this implies integral diverges. Therefore, the series diverges. By the integral test. Okay. Very straightforward. Okay, this test is really appealing because then you don't have to deal with the series anymore. Right? People are scared dealing with series, so they just do the integral. But remember that the chance that you can integrate a function is 0. I'm not exaggerating. The probability of a function being integrable, meaning that you can evaluate its integral and get an answer, is 0. Meaning that, again, almost no function can be integrated. Finding antiderivative is really, really, really difficult. I told you guys, there are people who study, they do their dissertation on integrals, solving only one integral. And in the end, they can't find a value for that integral. Very difficult. Okay, so the integral test applies. Yes, it does apply to the problems in the book, but in reality, if someone gives you a random series and they ask you to use the integral test, you won't be able to, because integrating the function is not easy or can't be done. Oh, yeah, Alexei, no, that's, I would probably put that, give that as an assignment, but no, we don't use the integral test that way. Okay, so let me see if I can, if we have enough time to prove the theorem, and then we'll do more examples tomorrow. I already have proven the test, but there are so many figures that I just don't feel like drawing. I'm just gonna copy this and use it. Let me leave that over here. Okay, so yeah, I want to prove you guys should be comfortable with the proof. Now you know the relation between a series and an integral. Okay, so yeah, if I don't finish the proof today, we'll finish tomorrow. But I want to do the proof because there's an inequality in the proof that is very interesting. Yeah, I could go without the proof, but I want that inequality. I want to show you guys where that inequality comes from. So when I use the inequality, you're not confused. Okay. So let's say we have again a series with a sub n equal to f of n. Okay, satisfying the three assumptions. Decreasing, positive, and continuous. Okay. Yeah. And again, what I've done here is I have graphed f of x. This is the graph of f of x. These are graphs of f of x. And again, the area under this curve is the integral of f of x. Okay. And we're going to construct an inequality and basically use the squeeze theorem, I believe is what we are doing. Okay. So let's just focus on this middle picture. Okay. We are looking at the area under the graph of f of x. Okay. From 1 to n. I'm not doing this from 1 to infinity. We're just looking at the area from 1 to n. So we will construct an inequality for or on the interval 1 through n. And then later we'll take limits. We're going to take a limit as n goes to infinity, and that is going to give us an improper integral. So the middle picture right here is the integral from 1 to n of f of x dx. Integral is the same as area. Okay, and I want to bound this integral. I want to find an inequality with a lower bound and an upper bound. All right. Now and by the way, so this is a graph of f of x, and again, these points are basically, that's our sequence function or the terms of the sequence. There are two ways that we can draw rectangles, guys. This is something that you guys did in Calc 1 or Riemann sums. You can inscribe rectangles or you can circumscribe rectangles. There are two ways. Okay, one of them gives you a lower bound, one of them gives you an upper bound. All right, so let's look at this figure right here. You can draw a rectangle over each interval so here is the interval from 1 to 2, the sub interval from 1 to 2. you can draw a rectangle using the left end point, go up from the left end point, draw a rectangle, or you can use the right end point. For this picture, I have used the right end point. So from 1 to 2, start at 2, go up, you hit the curve, then draw a rectangle over that interval. Okay, that's the left end point. And the length of that rectangle is not A1, of course, it is A2. See, this here is A2. Okay, and likewise on the interval from 2 to 3, start at 3, go up, draw a rectangle. The length of that rectangle is A3. Okay. Yeah, so if I write that series down, it'll be A2 plus, so again, A2 times 1 is the area of the first rectangle plus A3 times 1. A3 times 1 is the area of the second rectangle. Next one would be A4 times 1. And that is going to go up to the last rectangle, which is over the interval from n minus 1 to n. Again, we're taking the right end point, which would be a sub n, so plus dot, dot, dot. A sub n times 1 is the area of the last rectangle. Okay, I can write this as the sum where k goes from 2 to n of a sub k. We'll just write it in short. Okay, I can just leave it like that or write it in short using summation notation from 2 to n. All right, now if you compare these two areas, this area with the sum of the area of these rectangles, you can see that the green region has a larger area than the sum of the area of these rectangles, right? You guys do see that clearly, I hope, right? This total area is smaller than this total area. Okay, so we can say that this integral, or we could say the integral or we could say this integral is bigger than the sum of those, sum of the area of those rectangles. That's a sub k. Okay. Yeah, so this is what we call.
Is it k equal to 2 or k equal to 1?
K is equal to 2.
Yeah.
Thank you. Okay, so this is what we call a lower bound of this integral. Okay, tomorrow, well, we are out of time. Tomorrow we'll come up with this upper bound. And then we're going to take n to infinity, see what happens. Like, how does that give us the conclusion of the integral test? All right, but I will see you guys tomorrow.
Professor, are you having
Professor.
office hours today at 9:45?
Say what?
Are you having office hours at 9:45 today?
Yes.
Thank you.
All right, guys, I'll see you.